Welcome to class. Today I'm going to talk about ester enolates, and this is found in section 21.5 of your textbook. Before we get into new material, let's pause for a minute and review the mechanism that we looked at in the last lecture. And here I give away what that mechanism is, telling you that you need to think about a Dieckmann condensation reaction, also called a Dieckmann cyclization. And that is similar to the Claisen condensation reaction, only the Dieckmann is the intramolecular version of this. So the product of this reaction is ultimately going to form a ring. Here is the mechanism for how we got to that product. This is the carbonyl carbon of the ketone, and therefore there are two different alpha positions that we need to think about pulling hydrogens off of. If you pull the hydrogens off of this position, then ultimately it will lead to the formation of a six-membered ring. If instead you try to pull the hydrogens off of this position, when you try to plug that enolate into the carbonyl carbon of the ester, you're going to form a four-membered ring, which is thermodynamically unlikely. So we pull the hydrogen off here in the first step, forming the enolate. Then the enolate unloads into the carbonyl of the ester. The tetrahedral intermediate collapses down and bounces off the ethoxide, and we get to our final product. But just like the Claisen condensations and the Dieckmann cyclization reactions, because the solution is basic, you're going to continue to pull those hydrogens off and get to an enolate. And the reaction will stay here until you physically add in an acid in the laboratory to end up with your final product. The nomenclature of this compound is a little odd, and there's actually a couple ways of naming this, but the way your book explains is to treat it like a lactone, which is simply a cyclic ester, and you start from the carbonyl carbon of the ester and you count how many carbons extend out from that. So 1, 2, 3, 4, 5. That's where we get the pentanolide from. The fifth carbon is what connects back into the other side of the ester, and at the 3 carbon I have an oxo group. Generally speaking, the reactions that we're looking at involving enolates have two basic steps. The first step is that some base pulls a hydrogen off of the alpha position to form the enolate, and then in a second step the enolate collapses and unloads through the nucleophilic alpha carbon into an electrophile. And ultimately we end up substituting the alpha hydrogen with some other electrophile. And so far, the only bases that we've really used have been alkoxide bases or lithium diisopropylamide, and we've used carbonyls as electrophiles in the aldol condensation, the aldol addition, the Dieckmann cyclization, and the Claisen condensation reactions. What we want to look at next are alternate electrophiles. And so today we're going to talk about alkyl halides, and in the next lecture we're going to talk about using molecular halogens as your electrophile. So this is a conceivable reaction scheme where we take a ketone like this, treat it with a strong base, and then we add in an alkyl halide, and that will ultimately substitute off the hydrogen for an alkyl group. The mechanism for that reaction: this is the Lewis structure of lithium diisopropylamide without the lithium spectator ion. These electrons pluck off the hydrogen from the less sterically hindered position to form an enolate, and then the enolate unloads here into your your alkyl halide, then giving you your final product. And we've done pretty much everything here that we could. We pre-mixed our base and our ketone together to form the enolate, and then in the second step we added in the alkyl halide. We kept the base away from the alkyl halide, and yet we still only got 52% yield. And this is a reaction that your book reported. And to be honest, this is a pretty simple ketone. And if you get a 52% yield using a very simple ketone, you start to expect to get a much lower yield when you're using a more complicated ketone. One of the side products of this reaction would simply be the LDA pushing through the steric hindrance of the methyl group, forming the enolate on the other side and plugging in the alkyl halide on the left-hand side, but that's only 7% of your product. And so 7 and 52 is 59. There's 41% that's not being accounted for here. And this is kind of discouraging. So what we want to look at is an alternate pathway that allows us to solve the problem of poor yield. We still want to accomplish adding an alkyl group to the alpha position of a ketone, but we want to do it in a better way. And one of the ways we can do this is using beta-keto esters. And so just like with the Claisen condensation and the Dieckmann cyclization reaction, ethoxide can easily pull a hydrogen off of a beta-keto ester. The electron density cycles up onto one of the two sides, and then when the electrons cycle back down again, you add your alkyl group directly in. And this is a nucleophilic attack, and so the alkyl halide needs to be as unsterically hindered as possible. A methyl alkyl halide would be better than a primary alkyl halide, and tertiary alkyl halides probably don't work very well. One of the problems, though, you run into in this reaction is that this ethoxide and that alkyl halide were reagents that we showed quite a bit of their chemistry in the first semester of organic chemistry. And they react with each other, usually via an E2 reaction where the ethoxide plucks off a beta hydrogen to give you an alkene, or an SN2 reaction where it plugs in directly. And so how do you keep the alkoxide base and the alkyl halide from reacting with each other? Well, we run this in two separate steps. First, you add your alkoxide base to form your enolate, and then in a second step, you come along and add your alkyl halide. And this has pretty good yield so far. We've got the ketone right here. Adjacent, the alpha carbon has the alkyl group. Everything looks good except for this. If you go back to the original reaction, we just wanted a ketone with some type of alkyl group next to it. And here we've got the ketone, but we've also got this ester. And so what we're going to look at next is how to get rid of that ester. So at this point, we have added the alkyl group to the alpha position of our ketone. Now we need to focus on getting rid of that ester, and that's done in two steps. So it's two steps to load the alkyl group to the alpha position, and two more steps to get rid of the ester. And the first of those two steps is a saponification reaction. And this saponification is the base catalyzed hydrolysis of an ester. And the mechanism for that was part of the carboxylic acid family. We talked about all the hydrolysis mechanisms for that. But as a review, the hydroxide will come in and plug into the carbonyl group, bouncing the electrons up onto the oxide to produce the tetrahedral intermediate. And then those electrons collapse down and bump off your ethoxide. And now we have the carboxylic acid, but we have it inside of the container that is chock full of hydroxide. So there's no way you can stop the next step. That would be the hydroxide coming along and pulling a hydrogen off. And so we have an acidic workup that we have to do to put that hydrogen back on again. And I'm not showing those two steps right now. I'll come back to them in a second. So at this point we have, here it was our original ketone. We have placed an alkyl group on the alpha position. And there used to be an ester here that we just hydrolyzed to a carboxylic acid. This last step is called decarboxylation. And this is also a mechanism that we saw a while ago, that under high temperature conditions, anytime you have a carboxylic acid with a beta carbonyl group, it undergoes a retro-Diels-Alder-like reaction, pushes off carbon dioxide as a gas that floats away, and we end up with the enol. The enol will tautomerize to give us the ketone. So overall, what we've done is we started off with an ester that had a ketone at the beta position. So this is a beta-keto ester. And we pulled the hydrogen off of the alpha position, replaced it with an alkyl group, in this case an ethyl group. Then we did a saponification reaction where the hydroxide pushes into the carbonyl, electrons bounce up, come down, push off your alkoxide, and then we do the acidic workup and decarboxylate it to clip off the ester portion. And ultimately what we've managed to do is put an alkyl group on the alpha position of a ketone. And this process has 4 steps. The first step is the enolization step, and then we have an alkylation step, a saponification step, and a decarboxylation step. So I'm just going to call this the EASD process to help you remember these 4 steps. And this is one more time the same reaction scheme that we kind of walked through, where we start off with a beta-keto ester and we end up with an alkyl group at the alpha position.